All right, so we start again. So what were the 4 lines for training loop? Until convergence or epoch, compute J, compute grad J, update. We know how to compute J in both these cases. Until now we have talked about just 2 equations, 2 algorithms. What are they? Linear regression, logistic regression. Okay. So we have talked about right. So this particular algorithm is central to this course. At no point this will become irrelevant. Okay. By the way, anybody knows who had designed this algorithm? So gradient descent was devised by Cauchy. Cauchy का नाम सुना है? Right? अगर complex analysis पे course कर रखा है, right? Sorry? Huh? This was in 1846. नहीं, Cauchy को award की जरूरत नहीं है. So this was in 1846 if I remember it right, but around 1850s. So an algorithm that is central to modern day AI was designed in 1850s. Now J is something that we said that for linear regression it will be mean squared error, and for logistic regression it is what this is called binary cross entropy. Yeah, so maybe naam likh dena bhi makes sense. So this is binary cross entropy. Now once we know what is J, can we trivially compute J? Once you know what is J, once you have decided J is this or that or something else, you can trivially compute J? Yes. Problem lies with computing grad J. How do you do this? How do you do this? You compute grad J using an algorithm called backpropagation. Now backpropagation, it is disputed, but because some people accuse Hinton of copying it from someone else in 1950s. Now backpropagation as we know today, I should have not said anyway, so no, but it does not matter, this is a dispute anyway. So backpropagation was first seen in 1982 and then in a 1986 paper. So this is the version that we know today that uses dynamic programming to implement backpropagation. Okay. Now in the words of Hinton back in those days when they were saying what will happen to machine learning, because not everybody was doing it was a very small set of people were working on it, people like Hinton who had been working on deep learning since 1970s, right? Now, so he said that people used to talk about that algorithms will improve. Maybe we will start using something other than backpropagation or whatever, right? But it turns out you use the central algorithm is the one from 1850s, Cauchy, okay, gradient descent. Backpropagation is from 1980s, and in today you don't have a replacement of any of these two. So these two are still completely central to machine learning. In fact, they are becoming more central because earlier you used to do still something else. In today's world, all you do is neural networks, and these two algorithms are central to neural networks if you want to do any learning on them. So 1986 paper, backpropagation was there since 1986. Why is it that machine learning or deep learning took off in just last decade? Yes. Right, data. What else? Hardware improvements, right? So one of the most important laws that has resulted into AI today is Moore's law. What is Moore's law? Right, so transistors on chip, they double every 18 months. And this is something that has been true for last 5 decades. So for last 5 decades, you see the exponential trend in terms of compute, right? My mobile today is maybe faster than supercomputer 30 years ago, right? So increase in compute, increase in storage. If you search on Google in 1945, right, they were teleporting I think 64 kilobyte memory through a plane. In 1945, T.J. Watson had said, maybe in this world there will be a market for 5 computers. Today a single person has 5 computers, right? So high compute, storage, memory bandwidth, what else? Bandwidth. Right, better algorithms, yes, of course. Okay. Internet has played a very vital role. Internet was ARPANET back in 1970s, then it became NSFNet, and then NSF basically made it private in late 1994. So starting roughly 1995, we have seen this internet era, and once we have internet era and all these smartphones, the amount of data that we are creating each day, that fuels all these machine learning algorithms, and hence we see the same good old algorithms, but now they have compute and data. Okay. So coming back to this, what is backpropagation? I won't do it in this class, okay. I will do it after we will be done with a little bit of neural networks. So what is backpropagation? It simply helps you compute grad J. But computing grad J was not that big a deal for linear regression or logistic regression. How will my gradients look like for linear regression? We had done it before, right? So this was grad J. Now this was for just one variable. We had done this for just Wx. If you have Wx plus b, how will my grad J look like? See, this was actually grad J dj by dw because we had just one variable w. Now if we have two variables w and b, how will you compute this vector that we have been talking about? How will I compute this vector now? I want to compute all these derivatives, partial derivatives. How will I do that? Can you give me for linear regression just by looking at this particular equation? See, this is the coefficient of w. Coefficient of b is 1. So you replace this by 1 and this is what you have. So what happens if you have a n plus 1th dimensional linear regression? Del j by del w1, this part will be same and you will have here x1. Then del j by del w2, this part will be same, here you will have x2 all the way until xn. So del j by del xi will look like this part and then xi, okay. Now this xi is not same as that xi, there you will have in the subscript I, So maybe I should use some other variable, let's say j. Okay. So this is what we have. So how many these equations? This part will be common, and whatever you see here wj, then you will have here xj. When you have del j by del b, you will have this as 1. So you already know gradient vector for linear regression. Any questions here? Maybe you can do this again. If you are not following whatever I said in last 2-3 minutes, do this again quickly. Do this again quickly, and you keep here, you know, एक बार you forget i's. Forget these i's, just do it on one example. w1x1 plus w2x2 plus b. I am not even asking you to do it for all the way until n. Okay? Quickly कर लो एक बार. And I give you no more than 30-40 seconds for this. So you will have w1x1 plus w2x2 plus b minus y whole square. So when you will differentiate this, everything will come out. The only thing that will remain here is, so when I am computing del j by del w1, the term with w1x1 will remain, everything else will be 0 because it is a partial derivative, right. So, and when you will differentiate this term with respect to w, what remains is coefficient of w, which is x in this case, x1 in the other case. So you know how does my grad j look like, right. What is grad j in case of logistic regression? Right, so still my question remains the same. How do I compute? So we know how to, so we have put a for loop for epoch, we know how to compute j, and now we want to compute grad j. How will grad j look like in this case? So can you help me draw this vector grad j in this case now? Grad j. In this most general case, it will be right. This is what will happen. How do I compute each of these quantities? I am not going to do this here. Okay. So this I leave as an assignment, as a homework. Okay, you can write this as a homework. You don't have to show it to me, but you have to do it. So let us just look at this. As I said, I won't do it. So now let us say if I want to compute del j by del w1. Forget these examples, just look at this particular equation. Okay. Think over, and what will be y hats here? They will be actually sigma of z. So here you have chain rule coming into picture now. Okay. I won't do it here, I will do the backpropagation algorithm when we will do neural networks. One more thing that we should emphasize upon, both these algorithms. By the way, what is this algorithm, I mean what is this cost function called? Binary cross entropy. And what do you call if you have multiple labels? क्या बोलते हैं उसको? TensorFlow में नाम है ना उसका एक. Cross entropy term comes, but since it is not binary, there is some name, but right. So check it out maybe. Multi-class cross entropy, something like that. Okay, so we know how to compute J, we know how to compute grad J, we know how to update, so everything is settled now. Now we come to neural networks. Multi-label, okay. Multi-label binary? No. It has to be multi-class. It cannot be multi-label binary cross entropy, right? All right, leave it. Now we come to neural networks. Have we already covered neural networks? Yes, sir. Yes. Right from the very first day, what we are doing is neural networks. Now, what was our simplest neural network? I had this X and then output was Y hat, weight was W and bias was 0. I mean the simplest one, right? Bias was 0. Have we already done this? Yes. So I don't want to be doing this now. I have this now. Okay. One more thing. Unless stated otherwise, I now mean every neuron has two parts, linear and non-linear or activation. So every neuron has that. Okay. For this simplest neural network with two hidden layers, right? So now this is input layer. This is my output layer. Anything in between is hidden layer. Okay. So in this case, how many hidden layers do I have? 2. And this is how many layered neural network? 3. By convention, you don't count input one. Okay. Now if you see here, hidden layers are nothing but these hidden networks are nothing but the function, right? This is the function that maps input to output, right? And as we have said before, this function you can't really have any guarantees on it. You can't prove this is the best one, you can't prove this is the worst one, you can't even say something is better than other for all data set. Why can't you say so? See, you can't even say that this function works better than some other function for all points. Why? Because everything is data set based. You can say it for that particular data set, that on this particular data set this function works better than the other, but the moment you start getting new points, you have no idea which one will work better. And why do we do machine learning? To generalize well. Okay. So basically in this stream, no guarantees, no mathematical bounds, nothing. This is your guess, and if you are good at guessing how to fix these intermediary things, you will come up with models that are. So what is happening in last 5-10 years? Right? Let's say you were using RNNs for. So we said that you can't use feed forward neural networks for sequence data, then you started using something else. We'll see they are all the same thing, just that you manipulate them in some other manner. Okay? But everything else is the same thing. To me, the course is over. The moment we computed linear regression, logistic regression, we are done. But what will we see later? You will have complicated J's. So if J's are complicated, then computation of grad J will be involved. So there we have to spend time. Okay? There are cases when you want to change J. I don't want these two J, I want something else. So then things become complicated. You come and say, I don't want to have a simple tabular data, I have a textual data. Things change. You say, I have images, pixels, things change. Fundamentally, it is a mapping from input to output. What you put inside is your choice. Okay? But that choice cannot be arbitrary, it has to generalize well. So now, tell me what is y hat. I am still doing binary classification, so I still want to say yes or no, right? Tell me what will be y hat. So if you see this y hat, I am trying to write as a function of x. I am asking you to give me what is f in this case. If you do 50 courses on AI or machine learning, this equation stays, right? In every machine learning course, you are trying to find this function f that generalizes well beyond your data set that contains x and y. So I don't have a y here, I have y hat because this is my prediction based on this f. Now what can go wrong? This f that my machine learning algorithm predicts, and most likely in our course it is neural network. In fact, everywhere in today's world it is neural networks. So this is my ML algorithm. If I am able to do so well that this f approximates the actual function in the real world out there, then actually I have a very good ML algorithm. If not, then this is basically junk, I need to improve. Okay? This is machine learning, that's it. Next, you have to give me what is this. So let me help you with this. See, so neural network is nothing but composition of functions, and composition of functions that you decide. Okay? So let me see what is this f. Wherever you see an arrow, you should have a weight, except this last one. Okay? This arrow shouldn't have been there, I should have simply written y hat, but just for the sake of so this is, let's say, W1, this is W2. Okay? Just give me an example of a potential f. As I said before, and आप लोगों को इस बात से and you should be able to understand this by now, that there is no good, so there is no best f per se, right? All you can do is you can use a particular f and hope that it will work well. No, it has to work well for your data set, but in the end it must generalize well, right? Why I don't need a machine learning algorithm that does not generalize well? Because if it is good only on my training data set, for my training data set I don't need any machine learning. I have all the answers sitting there. Problem is I want to do it for a new point that is not there in my data set. So I have W1 X1, sorry, W1 X. How does that change to W1 X? How does that change to? So until now, where are we? Let's say first layer, so we have computed Z1. I don't want to go into this terminology right now. So just give me the composition of the function. So let's say nonlinear part is sigmoid. Okay. So let's say we are doing sigmoid here. Have we computed the output of this neuron? What will be the output of this neuron? W1X, and then you compute sigmoid of it. So we are here on this next one now. What do I do with this? This becomes input, so that gets multiplied with W2 here, W2 into this thing. Okay. Now that goes into a neuron again, assuming I am still doing sigmoid. This is my y hat. So this whole thing is my function. Okay. Good, bad, right, wrong, that's not what we are discussing right now. I am just showing you a simplest neural network. You can't have something simpler than this, other than, you can't have something simpler than this with non-zero hidden layers. Alright, now let me bring some notational jargons. So this is a how many layer neural network? 3 layer neural network. This is 2. Why did ऊपर 3 क्यों बोला था अपन ने? Right. This is 2 layer neural network. भाई output, hidden, input. You don't count input, so this is a 2 layer neural network. Right. This is my output layer, this is my input layer, this is my hidden layer. So ऊपर 3 कैसा आया था यार? Okay, so this was output. This was output, right? So this was output. And then hidden layer. अरे नहीं. This is my hidden layer. Okay? Right, so this is fine now. How do I write function for this? Trust me, जो लोग मेरे साथ नहीं लिख रहे हैं, they will have problems in exams. Unless you know this, unless you are following this, then that is fine. By the way, everything will be on YouTube. So, you have to give me this function now. Yes. Sigma of, so ab dekho, I'll introduce notational jargons here now. So x's are my inputs. Okay. Now I talk about z and then superscript 1. Write this down. When we have superscript 1 and subscript I. Okay. So in fact, let me not make it too complicated. Z1. Which neuron is, what is this? Linear output of output of first neuron of the first hidden layer, but I am not writing the here. So, this first goes here and this first is this one. Okay. I did not want to write I and J, that complicates things. So, first neuron, this one comes in subscript, and which layer comes in superscript inside a square bracket. Curly brackets, superscript, what we were keeping? So, what will this be? Maybe ith example in my data set, right? So, if in superscript I put I in parenthesis, then we are talking about example. But if we are putting in square brackets, then we are talking about layer. Okay. What else? I have A 1 1. What will this mean? You fill everything here. Z was linear output, so this must be, you can call it activation, you can call it non-linear. So, non-linear output of the first neuron of first hidden layer, everything is same except that you will have a non-linear thing here. Okay. Y hat, you know. Now, this notation is generalized for us. Okay. Whenever in superscript we put a number and in square brackets, that means we are talking about that layer. Subscript, we are talking about neuron in that layer. Okay. So, what is this guy? Which neuron is this? I mean, you have to give me the, okay, you are supposed to give me the output of this neuron. You are supposed to give me the output of this neuron that goes here. It is A11, first layer and first neuron. What will be the output of this guy? A12. And if I have n such things, A1, 3, A14, A1, n. What is this guy? A21, right, where 2 is in here, but since you don't have other numbers here, you can simply call it. So now see, input, I mean the linear output of this guy is Z1, 1. Non-linear output will be A1, 1. Z1, 2, A1, 2, and this Y hat is nothing but A2. Everybody is okay with this?
जैसे जो मेरे नोटेशन लिखे हैं उसमें लिखा है कि फर्स्ट हिडन लेयर मतलब लीनियर आउटपुट या नॉन लीनियर आउटपुट ऑफ फर्स्ट न्यूरॉन और फर्स्ट हिडन लेयर,
राइट.
तो जैसे वो A2 आता है तो वो सेकंड हिडन लेयर नहीं हो जाएगा, तो वो हिडन लेयर तो नहीं होगी.
Okay, so let me just keep it layer. Okay, but first hidden layer is actually my first layer. Done. Now, what function does it compute? Same as before, Now instead of single variables you have vectors as inputs. Okay. Okay. Now I won't go into the details of it, but there is something called universal approximation theorem. This theorem, now since it's a theorem, so it will have its proof as well. Universal approximation theorem states you can approximate any arbitrary function f using just one hidden layer. So you don't really need, these tens of or maybe hundreds of layers that you have in these big neural networks these days. But nobody knows how to get that function using just one layer. Moreover, the number of neurons might explode exponentially in that particular layer. So we don't know, it's an open problem. How do you increase the number of neurons in just one hidden layer to get the same function? So there are two ways of getting that same function. What are they? I mean, in the end what you want is y hat equal to f of x. So universal approximation theorem says all you need is one hidden layer. So you can have just one here. The way we are doing machine learning today, how are we doing it? Deep neural networks. So maybe hundreds of hidden layers. Okay. So universal approximation theorem says you can expand the number of neurons in just first hidden layer. Today's practice says don't expand in this direction, expand in this direction. So we know how to do this. We have no idea how to do this. Okay. So as the field advances, maybe we will see something here as well. But in today's world, the way we are doing it is we are taking compositions of compositions of compositions of compositions of functions all the way until maybe 100 times, 200 times, and then it turns out that we are able to learn billions or trillions of weights like in GPT-4 and so on, that it does what it was supposed to do. If you have this, you have to tell me the number of parameters in this particular neural network now. No, without bias, yeah, that's a good thing. So let me, that will be a good finishing point. Let us try to compute what everything is doing. So what is first neuron doing? I want you to help me figure out Z1. What is Z1? W1, X1. Now, right? Else it wouldn't make much sense. They won't be neural networks if not so this will not be a fully connected neural network. These two things have to be there. So now is this sufficient? No. You need to have W2, X2. And then how many number of biases do you have? As many number of, so number of biases equal to the number of neurons in the network. Okay. So there will be a bias here, there will be a bias here, there will be a bias here. Okay. These are inputs, they are not neurons. So 3 biases will be there. Let me call this one as, and let me know if you understand what is this. So what is this last thing? एक बार इधर देखो. What is this last thing? Bias in first hidden layer for first neuron. Okay. Now I will write here Z12. Sorry? Did I make something? बताओ भाई. So this guy is W1 x1, W2, no, no, no. So let me try to do this. Let me call this W11 and this guy becomes W12. ये 2 1 होगा? Sure? Right. So this will become W11. We'll fix it later. Okay. This for the time being, maybe you are saying right. Okay. But let's fix this later. So W11 x1 and W12 x2 plus B1. What is this B1 and what is its coefficient? Coefficient is 1. Okay. For other weights, coefficients are your inputs, but for this guy coefficient is 1. That means this parameter is independent of. So even if you have all these parameters equal to 0, you will still have something non-zero because of this. Okay. Now what is this guy? What is this guy? W21 x1. So W21 x1 plus W22 x2 plus B1 and then 2. Okay. Now these are the linear outputs. So what will be the actual output of this guy? This first one? What you will have is A1 1 that will be sigmoid of Z1 1. And similarly A21 will be sigmoid of Z2 1. Make sure I've done it right. Is this fine? All right. What happens at the next layer? No, but now you have to give me the equation. See, you have to give me equation for this guy now. This layer is done. You have output of this layer. Now, what goes next? I will need weights again. Okay. So, let me call them W3, W4. Or shall I introduce notation there as well? So, you can, this notation works for everything. If I write W12, that means it is the first weight of second layer. Okay. So, I will come to that, but not right now. Right now, I will assume this to be W3 and W4, let's say, or in fact I will use them W1 and W2 because they are still not there anywhere, right? The others were W11 and W12. Now, this is like a logistic. See, everything is like every equation here is a logistic regression equation. You have a look at it. Now, what will be A2? Sorry, before A2 I need to compute Z2, and since there is no other, I am not keeping any subscript here. So Z2 will be W1 A11 plus W2 A12 plus B2, right? Now my output y hat, which is same as A2, is nothing but sigma times, sigma of Z2. This is the computation of my whole neural network. We had just 2 neurons in the first hidden layer and 1 output. It will be insane if we start writing it like this for 10 neurons, right? So what do? Vectorize. So I'll get rid of subscripts now. How much time do I have? 2 minutes. So just give me a matrix that gives me computation Z1, Z2. So just tell me if I am right. If I am wrong, then we stop. W1 becomes W11, W12, W21, W22, right? And then this guy will be multiplied with X1, X2. So W11 X1, W12 X2, right? Plus B1, B2. Is that right? So, एक second, this is wrong. This is my Z. In fact, this is Z1, which is same as Z11. So we have vectorized things now. Okay? This whole matrix we can call W1. Okay? And this whole thing we can call B1. So this guy becomes B1. Quickly give me what will be A1. A1 will be sigma of this one, operated on vectors. What will be the equation next one? यार क्या बोल रहे हो? इसकी रैम ना. Anyway, so quickly, what will be A1? I'll write A1 here only. So A1 is sigma of Z1. Everything is a vector now. What will be Z2? What will be Z2? By Z2 will be W1, W2, this matrix times A21 and A22 plus B2. A1 आएगा. Okay. So this will be A11, A12, right? This is 1 cross 2. This is 2 cross 1, gives you a scalar 1 cross 1 plus 1 cross 1 Z2. Take sigmoid of it, and what you get is y hat. Okay, we are done for today.